learn from everything you fail, right?
Yeah. Okay, so we will go ahead and continue. So what we're going to start into now, once we can kind of get settled here, I know that quiz was awfully exciting. We're going to look at the PSS section in Chapter 7, or sorry, Edition 7, which is also known, I believe, as Chapter 2. In any earlier edition, maybe, at very least in the 6th edition, it's Chapter 2. All right? So I'm actually assigning homework questions now. Most of these, again, still don't show any work. But I'm kind of tired of this not really having anything to write down, so I'm going to make you guys write some stuff down. Okay? If I got to work, you got to work too, right? So what I want you to do is write out the question as well as your answer whenever you go through and do these. I'm pretty sure in all of these cases the question is fairly straightforward. You do not need to make it some big, long, every single word. You can just write a few notes saying what the question is. Okay? As long as it's fairly clear what's going on. These questions are picked from Edition 7. Okay? So if you don't have the 7th edition, what you're going to want to look for are the key words on the far left. So I've got 3 questions based on measurements and uncertainty. So look through your question list and try and identify questions that ask about measurements or uncertainty. Significant figures. They didn't actually have a whole lot of questions on that, which I was kind of surprised on, at least directly. So there's only one question there. The rest of this is rounding, then math and more rounding, and then exponential and scientific notation. Okay? I will post these questions. Since I'm seeing some questions about it, if you're trying to find the questions for these, if we flip open, I'm going to steal your book. It's okay. I will give it back. If you flip open to PSS in your chapter or your book, take a look at the very end of that chapter. You've got all the questions. So in Edition 7, that is page, I'm sure I'm looking at it right? 25? Yeah, 25. Okay, so if that's what you're using is Edition 7, flip to page 25, and you'll see all the questions listed there. I'm sure I did this right. Yes, I did pick all the odd questions. Any ideas why I would pick the odd questions? Answers are in the back of the book. Okay, so the hope is that you don't just copy the answers, but that you work the problem and then check your work. Okay? That's how you should be doing everything for every single class. Yes, then yes.
Can I write all of that in the homework notebook? Like the question? Like
yeah.
The info? Okay.
Yep. Yeah, the homework notebook is very loose. You can take notes in it if you want. Just please label where you're actually answering questions so that I can find that information as quickly as possible during the exam. Okay? I did just pick these questions as of 7 o'clock this morning, so they didn't actually make it into the slideshow. I will post an announcement that has a running tally of all the questions and what chapter they're referring to and when that homework section is due. Okay? When is your homework due? On the day of the exam. Okay, so I'll even put the due date in the announcements as well to help make that as clear as possible. Okay? Questions about the homework now that we actually have something to work on?
So this one required in handwriting, but the last homework one, just read through it.
This is the first homework set that I will actually look for on the day of the exam. So this requires actually writing something down.
So no matter how to think for like 1 or 3.
For chapters 1 and 3, there's nothing to write down for your homework. Other questions? I know it's a little confusing. That's my fault.
So this isn't going to be online right now?
This will not be online yet. After class, it will become online. Magically. Okay. I'm going to assume random chatting means we're done with that. So let's take a look at what's going on in that section. So what we've gone through so far and done is looked at all the qualitative comparisons, or some qualitative comparisons and ideas behind what's happening in each thing. Now what we need to do is come back to the quantitative. We need to be able to put some numbers to each of our experiments and our reactions and thoughts and ideas. Okay? To do that, we have to have an understanding of what those numbers are going to mean. So whenever we run an experiment, we almost always take some kind of measurement. Those measurements are what allow us to compare experiments between different scientists. Okay? So a measurement is going to include a number, and while that number is important, it's pretty useless unless you have the unit. Okay? So the most important thing that you guys need to be aware of when you're going through and doing any measurements or any calculations or anything along those lines are units. So as we continue to push through the semester, if you write down a number without a unit, I will take off points. Okay? You must identify the unit every single time. It is of critical importance to doing your calculations, and when we do more complex calculations, it becomes even more important. Okay? A lot of the questions that you'll see in this chapter, particularly when they look at math and stuff, will say, what are the sig figs? Don't answer this part of the question. What are the sig figs when we do this calculation? Okay, well, as I just said, you must specify a unit. What is your unit in this case? Okay, let's try the first part. Can we do the math? What's the math? We get 4, right? So you just wrote down a number. For you to write down a number, you must specify the unit. Do you have any idea what that unit is here? No, it could be meters. It could be kilograms. It could be seconds. Since you don't know what that is, and I'm going to try and push this into your head as best as I can now so we don't run into this issue later on, if you're going to write that number, the unit you're going to need to specify, if you don't have one, unit. Okay? It seems silly, it seems stupid, but I don't care. You're going to do it anyway. Okay? I want you to get in the habit of always writing a number with some sequence of letters thereafter. Okay? It will become important, I promise. Okay? So let's look at some possible units that we can come up with. So there's some common measurements that we can observe or make. We can get distances. At least that's what I called it, and then looked at the book, and they like to call it length. We can do mass. We can also bring in weight. There's a reason it's not bolded, though. Volume and time. Anybody know a unit for distance or length? Okay, I heard feet. Meters. Getting nitpicky with the centimeters. Okay. What else? Anything else? How far away do you live? Okay. What's the point of me listing all of these out? Well, because we're all humans and we very seldom actually get along, it turns out there's all sorts of different measurements that we can get or different units that we can bring into it. Okay? So we want to try and be as consistent and even as possible. If we were, say, actually I haven't taken an engineering class, but I'm going to keep beating on the engineers. If we were an American engineer, what units do we use? Really? Engineers use meters too? In the U.S.? Okay, well that's not fair. Which is good, it should be. What's a field that doesn't use those? Science absolutely uses the SI units. General populace, I guess. If you were going to measure distance or height of somebody, okay, in the U.S., what are you going to pick? Feet and inches. Okay? Which is nice, but where did those come from? This is the next fun part about all of these measurements. It was the king. The king came in and said an inch is now the distance of my knuckle, and I forget which knuckle it's supposed to be. On me, it's the tip of my thumb to that first knuckle. Okay? So if you ever get bored, compare your knuckles to everybody else in the class, and you'll find that they're not the same. So what happened when we dealt with inches in England? Every time there was a new king, what happened? All the distances changed. Okay? It's a pretty silly way to measure anything. Okay? So eventually we came through and standardized that and said, came up with what that inch was. Okay, so all of our units are an arbitrary determination. So the inch was based on that. Okay, what about feet? How'd you get feet? Size of the king's foot. Okay? In theory, that was supposed to be 12 inches. Okay? Maybe, maybe not, depending on the size of their feet. Okay? So again, we had to standardize these measurements. So somewhere, I think in the States we'll probably have one for this, there is a standard measuring stick that has exactly an inch and exactly a foot. Why do we need that standard piece held somewhere? Okay, well, what happens if we used wood? Okay, anybody know what happens to wood when the humidity changes? It changes its size. Okay, that's a bit problematic. Because again, every time the humidity changes, now my measurement changes. Again, that's a problem. So what they've done is built these standard units, and they built them in materials that tend to not respond very well to heat or humidity. And then they lock them up in a vacuum-sealed chamber and say, this is now the permanent measurement. So now we'll go through and always measure everything off of this. So all of our rulers are based off of this, at least in the States. Okay? One of the big problems with feet and inches, and the general science community, I think they had a better story for it in their book, said that this was a bit ridiculous to deal with these constantly changing units and these king-centric measurements. So what they went through and did is came up with a kind of a universal system. The intent being that you could easily compare all the way through. Right? Nice, simple relationships. It's not 12. Okay? Multiples of 12 can be difficult to deal with. Okay? So instead, they came up with something known as our SI system. And we look at your possibilities. We're looking at meters and centimeters. What's the common denominator, if you will, between those two words? Meters. So your standard measurement for distances is meters. Okay. So if we go back to the textbook, particularly the textbook's previous slides, they say our standard unit for distance is centimeters. Really, the centimeter is just a derivative off of the meter unit. Okay. How do we know that? What does centi mean? Okay. For a centurion or a century, okay, we're looking at hundreds. Okay. What is that relevant to? Well, what they did was took that meter unit and then divided it into subcategories. And they did those by factors of 10. Why 10? Easy was what I was going to come up with, and I got stumped there for a second. I'm going to run by, we picked 10 because 10 fingers and toes, or 10 fingers and then 10 toes. Okay? So we've seen these multiples of 10 before. It might just have been their easiest comparison. And then that's where we come up with these prefixes. Okay? We're not going to get too much into the prefixes yet. That's more chapter 3, 2, depending on what book you're looking at. Okay? So our standard distance measurement or length is going to be in meters. And depending on what we want to measure, we may change the prefix on that meter unit so that we can measure a little bit more appropriately. For instance, if you're going to measure something in class, right, anybody know roughly how long a meter is? Okay, somewhere in this range. If you want to measure the length of your textbook, meter's going to be the best unit? Not really. We probably want something a little bit smaller than that. So we could shift down to, say, centimeters, okay, or decimeters. Okay? Kind of just depends on what we want to work with. In our class, we're typically not measuring things on that scale here. We're typically looking at much smaller. So most of the measurements you'll see for distance and length will probably be in centimeters. Okay, but that's not our standard unit. Our standard unit is the meters. We'll start to scale it accordingly depending on what we want to measure. How about mass? Okay, now we're hearing a whole bunch. We got grams. I heard kilograms. We got pounds. Ooh, ounces. Ooh. Uh-oh. I'm going to just abbreviate that. All those U's and N's and Z's and stuff. Ounces. I won't worry about spelling that. Okay? You go with tons. What was that? Liters is not a mass, but remember that one for a second. So again, we have a whole bunch of different units that we could work with. Again, what we want to do is pick something that we can keep consistent across all measurements as far as the field of science and now apparently engineering too. Okay? Auto mechanics. Auto mechanics use a... Really? Are you killing me? Okay, I don't know. I was hoping to find somebody to pick on. I'm picking weird units.
Nobody does that.
Okay? So if we go through and take a look at this, what's our standard mass unit going to be? Looking at our grams. You might also see kilograms show up, but what's happening with that? What we're saying is that kilo prefix is again one of those multipliers that we're putting on the gram unit. Okay? And like I said, again, we'll evaluate what the kilo means at later time. So we're looking at grams as our primary unit. Okay? What about volume? Go back to liters. I like that. Good call. I was actually having a hard time figuring out other ones. Gallons, pints, quarts. Oh, I can make fun of people now. How about quarts, pints, and all that? What are those a measure of? I can't repeat that one officially. Okay, we could look at cooks. Okay, chefs. What are they doing with each of those processes? They measure. You'll typically see, at least in the States, pints, quarts, cups. Okay, why? That's because historically that's what we ended up using in those circumstances, and it's very hard to convince particularly old people to change their methods, okay, or change their measurement systems. Okay, so what's our standard unit here? We go back to our liters. Okay, how large is a liter? You buy Coke, if you're going to buy it in bulk, you typically buy it in what size? 2 liters. Okay, so that gets us an idea on what 2 liters is. Cut it in half and we got a liter. That's a fairly large amount of substance. So if you're going into the lab and I'm asking you to work with acids, okay, particularly corrosive acids, did this last afternoon too, that's not going to be a particularly fun thing for you to work with, because at that volume you're now being exposed to a much larger danger than if we used a smaller volume. Okay, so what's the more common unit that you'll see? Whoops, that's an eraser. Are there 2 L's? It's early. I'm blaming that it's early. We could use milliliters. What's going on with our milliliters? Again, that milli is our prefix on the liter unit. All right. Last one. We've got seconds, minutes. Now, okay, you get the idea. Of those, are we consistent across the world with our time? Yeah, actually we are. It's kind of interesting. A second in the States is the same as a second anywhere else. Any idea why? Just so you know, I'm making this up here too. What did you guys say? We could look at how the sun works. I'm going to guess it's going to come back to navigation. Everybody trying to navigate around the world needs to be able to tell somebody else when they got there or how they got there. A lot of old school navigation had to do with time and where the sun was and where the moons are. Okay? You need to have a consistent measurement of time so that you can then tell people, oh, it's going to take 3 hours to cross the ocean. That might be a bit of a stretch, but okay. Whereas if you tell them 3 and they go, well, no, it actually took me 40, some other weird unit of time. Okay? We don't have that comparison. Okay? So interestingly enough, time is consistent around the world. We're dealing with seconds, minutes, hours, and you can scale up larger and larger. Okay? As far as your labs, what units do you think you'd want to be using? Why seconds? let's think about your experiments. You go into lab, what's your primary goal once you go into lab? Now be honest, don't lie to me. To get out. Okay? If your experiments take minutes or hours, is that going to be a particularly fun day in lab for you? No, your goal was to get out of lab as fast as possible, which means we being teachers try and design the experiments such that we can get you in and out as fast as possible. So most of your observations will happen on the second scale. You might see a few jump into the minute range, but most of them are on seconds. Why do we not go smaller than seconds? What's that? It's harder to physically observe. Okay? So seconds is something that we can actually monitor. If something happens in 1 second, we can typically at least trigger that and see that that response happened that quickly. We won't go much lower than that because our eyes and our bodies can't physically respond on a scale that much shorter than seconds. Okay? Unless you're really fast reflexes. But even then, it's not that good. Okay? So we've got our standard units for each of our measurements. Would have been nice to come up with some way to abbreviate all of these, right? Because if we go through an individual experiment, and for each of your units, I told you that you have to write out seconds, or liters, or grams, or what did we say our distance was? Meters. Okay? You might get a bit irritated at how long that unit is. So what do we do being lazy scientists? We abbreviate. What are our abbreviations? CC is actually a different measurement. So for our first one, M, grams, capital L, and S. Okay? So when I ask you to write out a unit, you can come up and abbreviate things as quickly and easily as you want. You don't have to write out the full name of that unit. Okay? Seeing a lot of crossed arms. Okay? You guys must be angry at me. Standards were created to quantify these things. So we already kind of talked about this. There are facilities that then hold measurements of distance, of mass, of time. Everything always gets compared back to these. So if you ever use a balance and it doesn't weigh or it doesn't mass appropriately, okay, you might hire someone to go through and retest it and recalibrate it back to those standards. I forget where it comes from, but we do actually have a standard one for time. Anybody know what it is? What's the atomic clock based on, though? It's going off of some atom, I think. Yeah. So the time does have a standard measurement. Originally, we used the revolutions of Earth, and we tried to divide it up into subcategories. And then what we had to do was come up with something more consistent, because the revolution around the sun isn't exactly consistent. That does change. So time, we picked the decay of a single atom. Okay? And it's the amount, how much of it decays within a given time period. Okay. So we do have a consistent measurement there. Kind of interesting. Other questions? Okay, so now what we can do is take a look at some other interesting features of this. So if we want to measure the length of this metal rod, okay, what would you tell me the length is? Okay, and just in case, let's make sure I did this right. You can't quite see it. Let's go ahead and blow it up. What are you going to call it? Give me some numbers. 4.2. 4 point. Anybody else? Okay. Depending on who we talk to, we might get slightly different measurements on this. This brings up a problem. Okay? If we're trying to run an individual experiment and we go through and report the length of this metal rod and we now give it to somebody else to measure, if it's science, that result must be exactly the same. If it's not, we then assume that our process was wrong. Okay, so when we report numbers, there's another important aspect that has to come along with each measurement. It's not just the number. We're also going to have to report a measure of the uncertainty. That's going to make me sick, so I'm going to stop looking at those screens. Okay. So we also have to report how accurate our measurement is, okay, or how small of a number can we associate with that. Okay? So what do I mean by that? Well, what happens if we went through and now measured with the other measuring stick? What numbers are we going to get in this case? I heard a 4.2 again.
4.25.
Anything else? Those are the only two numbers you guys come up with, really? Come on, work with me. 4.26, there you go. Okay. Price is right, just add one. Okay. Interestingly enough, you guys are actually relatively nice. I didn't hear any 2s or 5s in there. Okay. It's a nice, good measurement skills. Okay. What happened with our measurement? In our first case, we had a couple 4 zeros. We had a 4.2. We had a 4.15. Okay. If we go through and now compare our numbers, the numbers off of our second measurement include an extra decimal place. Okay. Which means we increase the accuracy, or we increase the amount of information in that measurement from the other one. So what we're looking at is starting to get into the idea of significant versus insignificant digits. Why did no one give me 4.2639652? Okay. You don't have anything to compare off of to get that accurate of a measurement, okay, or that precise of a measurement. Okay? So what we want to do is whenever we report a measurement, we also should report the accuracy. Okay? How close is our instrument going to get? That's what I mean by that. What we should do is report the uncertainty. So in our first case, if we went through and took a look at our numbers, whoops, come back here. We had, say, 4.1 plus or minus. We went back and looked at our numbers. We were probably about 0.1. When as high as 4.2 and as low as 4. Okay? When we include that information with our calculation or with our numbers, whoops, what's the big thing I forgot? Units. What units should we put on this? Did it say centimeters on it? Okay, good. I didn't actually remember if I left that on there or not. Okay? If we moved the other one, what did we get? Everybody nailed down 4.2. So now when we look at our accuracy, we're going to shift a little bit lower. Okay? Deciding exactly what that accuracy is, what that number is a bit more challenging. Definitely didn't see an explanation of it in your textbook, and I'm not sure I accept this analysis, but this is what the textbook slide said. Plus or minus 0.05. Okay? What that is a measure of that last digit. Okay? What's as accurate a number as possible on there. In our second measurement, we know for sure we're looking at 4.2 pretty darn accurately. For our first one, 4 is pretty much as accurate as we get. Why do we include that last number? Did the instrument give us that number? Were you able to record that information? Could you decide what that number was? You had some information there. It may not be super accurate, but you did report that information. That gives us a little bit more information than if we'd just said 4. Okay? So we always want to report to the absolute maximum number of decimal places that our instrument gives us, because it gave it to us for a reason. It may not know exactly what that number is, but it is a reasonable approximation. Okay? We don't take it further than that, because what's happening at that point? Now you're straight up guessing. There isn't really anything to measure against. You are literally just guessing at the number. Okay? There is no information or no evidence to support that additional number. Does it kind of make sense? Okay. So what we want to do with these is be aware of the errors within each of our instruments or within each of our measurements. Okay? You will see more of this when you get into the lab. In most cases, at least that I've seen in any experiments that show up in undergraduate labs, these errors are typically ignored. Okay? Realize that they are there. If you move through larger, or not larger, move further through the fields of either chemistry or science, you will have to start being aware of these issues. Okay? In most cases, the instruments are calibrated to such a huge number of digits that we don't care about those last digits, and the error associated with it doesn't affect what we're actually doing. Okay? That said, my research involved a whole bunch of different calculations, and the error seemed relatively small on each number. What happens when you then have to do calculations with each of those numbers? The error propagates through the calculations. Again, that's a more advanced class. So what was the end result of my experiment? Effectively, I came out with my answer being 2 seconds plus or minus 5 seconds. Okay, think about that. That means I either had negative time or way positive time. What does that mean about the accuracy of my experiment? Pretty useless. Okay? My advisor insisted was wrong, but he was wrong. Okay? So we want to be aware of these errors because that lends credit to the measurements that we're making. Okay? So when we go through and take mass, it's a measure of the amount of matter that it contains. And this can be easily confused with weight. Mass and weight are different things, even though they are typically used interchangeably. Weight is something that is affected by gravity. Mass is not affected by gravity. Okay? I will always have the exact same mass, no matter where I go in the universe. My weight will potentially change. Well, where's the biggest confusion on that? When you step up onto that scale and try and figure out what your weight is, or what we classify as weight, really it's not measuring weight, it is trying to approximate your mass. Okay? And your balances are an approximation of that, okay, your scales. If we take a look at what we use in the lab, each of these will always measure the appropriate mass. Okay? It doesn't matter where we take these balances, they will measure mass. How does that work? Well, in the very top one, what we've got is what's known as, does anybody know what it's called? Okay, that's what I was going to call it too. Triple beam balance. Why would this measure the same mass no matter where you went? Because we're going to put our object on this side, and it's going to push down, and gravity is going to pull that thing down. How do we figure out the mass on this? We take these little weights and we shift them this direction. Okay? What we're doing to measure the mass is we are comparing both the force of our object pushing down, but also the force of each of those other individual masses pulling down. Which means if we change gravity, they're both getting pulled down now at a different gravity force. Okay? But the mass is still the same. So what we're doing with these balances is always comparing them back to a standard mass. When we move that little block, okay, we have a standard mass for it, and we apply different physics rules to each of those unit calibrations along that slide, and we know that that would represent 10 grams, okay, or 5 grams. So it's a direct comparison. We don't just put an object down and just say, oh, that's what it weighs. Okay, what we're doing is we're directly comparing it to something else on the balance. And what we're assuming is that something else was measured accurately. How do we know it was measured accurately? they go back to the standards. Okay? So our manufacturer presumably went to the standards and say, okay, I need something that gives me this mass. And they built something that generates that mass so that they can now build these to always compare back accurately. Okay? Remember, we're always comparing back to something that we have decided to be the standard. Volume measurements. We've got a variety of different ways that we can monitor volume, all sorts of different scales on our units, and again, different accuracies. The most common one that you will probably see in the lab will be the graduated cylinder, though you will work with the burette, pretty sure, in this semester. You might see the pipette, and you might see the volumetric flask. Why do we use different instruments to measure the volume? Comes back to the accuracy of the measurement. Okay? Do we really need to know it out to 6 different decimal places? Well, if we need to know that kind of accuracy, we have to then go through and make sure the instrument that we're using to measure that gives us that accuracy. Okay? So you got to be careful with what you're trying to do. In most cases, the graduated cylinder is good enough. A lot of people will use syringes, particularly if anybody's in the nursing field, or I guess any medicinal field, doesn't have to be nursing. What's the standard measurement when you're dealing with syringes? cc's. What does cc stand for? Cubic centimeter, which also happens to be 1 milliliter. All right, why they switched it to cc versus ml, I don't know. Maybe they like the way cc sounds better. It's not a bad idea, actually. cc does sound a little bit easier than ml. Okay. Significant digits. Okay, this one gets particularly fun. Okay, when we record our different measurements, we need to report what digits are significant. Okay, and that last digit is really what allows for the uncertainty in your measurement. Okay? So what we need to know is, given a sequence of numbers, what makes that digit significant. So now what we're going to do is just look at a sequence of numbers and try and figure it out. Okay? So first off, our first rule, numbers 1 through 9 are always significant. Doesn't matter. Those numbers are always going to be significant. You must count them as a significant digit. The tricky one is 0. Okay? And to figure out what's going on with 0, we really need a little bit more information. And that more information is typically found in the decimal point. Which means whenever you're going through and doing your experiments, you should specify the decimal point, because that removes all ambiguity about what 0 means. Okay? And there are going to be different rules applying to it. Problem with that is that since we're in a lecture with the textbook, you aren't doing any experiments. So you've lost the information that an experiment would give you, which makes this a lot more difficult as far as you guys trying to interpret it. And you move out into the real world, your significant digits become obvious, if you will, because you're working with it. You can see them on the instrument. When it comes to the textbook, we have no idea what that measurement was about or what made it. We have to be able to interpret those numbers appropriately to figure out what digits are significant. Okay? If there is no decimal point, the 0 must be controlled by numbers on both sides of it to be significant. Okay? So in that case, what we're looking at is our very first example. How many significant digits are in that number?
3.
All sorts of fun answers. So first off, rule number 1. All digits 1 through 9 are significant. Is 1 one of those digits? Yes, there's 1 significant digit. What about 2? Is that a significant digit? Yes. 2 is a significant digit because it is one of those 1 through 9 numbers. 1, 2, 3, 4, right? So we have 2 significant digits. Last one, 0. Okay, 0 is the tricky one, and it typically requires a decimal point to figure it out. So if we can shift to number 2. If there is no decimal point, for the 0 to be significant, there must be a number on either side of it. So it must be controlled or bound by 2 numbers. Where's the 0 located? Right in the middle between both 1 and 2. Is that number significant? Yes. How many significant digits do we have in 102? We have 3. Okay? So what happens in the next case? Now we've just shifted things around a little bit. Okay, 1 and 2 are still numbers between 1 and 9. So both of those count. We have 2 significant digits. What about the 0? Can I count that? For the 0 to be counted, I must have a decimal point. Without the decimal point, I have to have a number to both sides of the 0, both left and right. Do I have a number? No. Which means, how many significant digits do we get? 2. Okay. What happens with the next example? One of the big changes is we now have a decimal point, so we need to come up with a new rule. So let's shift to rule 3. If there is a decimal point, then a 0 only needs to be preceded by a digit to be significant. That means one of our numbers from rule number 1, 1 through 9, have to be in front of the 0. As long as there's a decimal point and that is satisfied, then it counts. So what happens in 120? Decimal point. 1 and 2 are both significant. We've got a 0. Do we have a decimal point? Yes. Is the 0 preceded by a significant digit? Is 2 a significant digit? Yes, which means how many significant digits? 3. Okay. Is that clear?
I'm not sure why it's 2 in the second one.
Okay. In the second one, let's go ahead and see if I can highlight that with purple. Let's pull that out again. Follow our rules. Rule number 1, all digits 1 through 9 are always significant. Is 1 a digit between 1 and 9? Yes. So there's 1 significant digit. Is 2 a number between, or a digit between 1 and 9? Yes. There is a second significant digit. Now we have a 0. Okay? 0 does not fall under rule 1 category. Okay? So we got to move to rule 2. If there is no decimal point, so look at our example. Do we have a decimal point there? No. Okay? We cannot imply decimal points. Mathematics is very black and white about that. Okay? The decimal point must be specified. Otherwise, we have no idea what's going on with it. If there is no decimal point, then the 0 must be bound by 2 significant digits, both 1 in front and 1 after. If we take a look at our 0, we do have a number before it. Okay? Do we have a number after it? No. Which means it is not controlled, which means we cannot count it as significant.
But isn't the scientific notation going to be the same for both of them? Like,
No, technically not.
no.
Yeah. We'll get into that when we move into scientific notation. Okay? I know, it's a bit of a tricky concept. Let's add one more thing here just to test this, because this is, in my opinion, the tricky version. Let's add another 0. 1 and 2, both significant. That 0 right in the middle, the one that I didn't color in, is that significant?
The middle one is the first one.
Okay. For the middle one to be significant, it must be bound by a significant number. Go back to rule number 1. What are the digits that are significant? 1 through 9. Is 0 a significant digit? No. That means that last 0 I drew in there, even though there's a number there, it is not a significant digit. Which means, whoops, sorry, that one. Which means that 0 is not bound. It only has 1 digit that is significant next to it. Okay? What is that? 1200. Still only has 2 significant digits. Only 2. Yes?
So the definition of number 2 should change a little bit then. Because it just says controlled by numbers. It doesn't say by significant numbers.
True.
So that, to me, that's
Yep.
I was confused because by that definition.
That is
of number 2,
absolutely accurate. Let's go ahead and fix that. Must be controlled by significant digits. Significant. To be counted as significant. It just says numbers. That is absolutely valid. Good point. Okay? that make sense now? Everybody on the same page? Okay, what do we got? 40? Okay, what happens with now our very last, or sorry, the last one in that column? 120.0. 1 and 2 are significant. What about the 0? The middle 0? Yes, why? We have a decimal point and it's preceded by a significant digit. Okay, so that 0 counts. What about the very last 0? The 0 before it. Was the 0 before it considered significant? Yes. If we move to the next 0, there's a decimal point. It doesn't say anything about where the decimal point is. If there's a decimal point, that has to be preceded by a significant digit. What's in front of it? A significant digit. Which means, how many significant digits do we have in that last case? We have 4. Whoa. I know, I was fixing it. It skipped on me. We've got 4 significant digits there.
Can you explain to me what it is?
Okay, so let's go through that one once more. Oh, man. And I'll see if I can't write this out. Significant digits are a pain, I'm not going to lie. Though, in my opinion, I like my explanation better than the textbook.
Yeah, I was just getting there.
So let's go through and take a look at our last number here, the 120.0. Okay, 1 and 2. God, why? Let me draw. The 1 and the 2 are significant. Okay, so we can identify those. The next part is the 0. To determine the significance of 0, does it count or not, we have to go back to rules 2 and 3. Rule 2 was if there is no decimal point. Do I have a decimal point? Yes. So rule 2 is irrelevant. Move to rule 3. If there is a decimal point, then the 0 only needs to have a, and this is where I actually got lucky with my phrasing here, it just needs to have a digit in front of it to be significant. Okay, we could technically call it significant digit in front, but it doesn't matter. Okay, so let's go through and take a look at our 0. Now let's go ahead and highlight it and box it in as purple. Is that 0 significant? I have a decimal point and it is preceded by a significant digit, which means yes. So we can underline that as a significant digit. Move to the next 0. Is there a decimal point still? Yes. Is that 0 preceded by a significant digit? Yes, which means that 0 is now significant. Okay. Why do we define it as being significant? It's going to come back to our rules behind how we measure things, and it has to do with accuracy. Because in the real world, if we went through and evaluated how we got these numbers, it would come down to mass, okay, or any measurement. But now when you propagate your calculations, which we haven't gotten to yet and we won't get to today, if you go through and run the calculations, if you don't include that 0, you lose accuracy in your end result. Okay? So what you can do is propagate, let's see, you don't want to look at exact. Okay? What you might do is shift to these rules, looking at how we then take that measurement and manipulate it. Do we add it to something else? Do we multiply it to something else? How does that affect our end result? Okay? If we don't record that number as significant, we lose massive amounts of accuracy in the result, which we will see when we go through the additions and subtractions. Okay? So it is a necessary step to include, okay? And that's why. It goes back to the mathematics.
The second column relate.
So as you guys are leaving or packing up, which is fine, let me go through and just write down the numbers real quickly. 0.12 has how many significant? 0.12? 2. Why 2? We do have the decimal point. There's no number preceding the 0. That 0 does not count. Next one. 2 again. We still have those 2 zeros. Neither of them have a significant digit in front of them. Last one. 3. Now we have 3. We can count that last 0. because they have a significant digit preceding them. Okay? So we'll pick up there. When? Tuesday. Tuesday next week.
Wait, so basically if it's in the